Hi guys, so I think that's going to be the last video of this series. So today we're going to talk about thermal expansion. So when temperature is going to increase, material will tend to expand. When temperature decreases, the material will tend to contract, except for water. When you increase the temperature of the liquid between 0 and 4 degrees Celsius, water will contract. And then it will expand after 4 degrees Celsius when you increase the temperature. So you see, it can have devastating consequence, okay, if you don't pay attention to the expansion because of the increase of temperature. Okay, so that's why bridges, for example, they need to have those expansion joints. Okay, so for example, when you go from this temperature to that one, you see by how much those joints will move. Okay, so you need to have those joints, otherwise you can have a disaster. So I have a nice picture here. You see, this is a bridge. Maybe it's a San Francisco bridge, I'm not sure. But you see the expansion joint here. Because when it's going to be hot outside, it will expand. And when it's going to be cool, it's going to be, it will contract. Okay. So before getting to the math, I always have in mind this event that happened in 1986. I was a student at the time, and it was all over the news. It was at the time of the golden age of the Space Shuttle. So it was a successful program by the NASA. 1986, they sent a group of astronauts, including one teacher. So I don't know which one it was. I don't know if it this lady or that lady, but one of them was a teacher. So it was she was part of a program to get students or kids more interested into science. I think she was a social study teacher in a high school. I think she was from New Hampshire. So it was everyone in the country had the eyes on the launch, right, of that space shuttle. The name was called Challenger. And then terrible event here, it exploded and everyone was killed. This photo was on everywhere, was everywhere in the world because it had the shape of a scorpion, right? So it has like the tail here, and there it has like the arms, like I don't know if it's called the stingers of the scorpion. Okay, so it was all over the news. So what happened back then? Actually, it's because of the expansion joint. So one of the booster had expansion joints, and the space shuttle was launched from Florida. So Florida usually has a warm weather, but that day it was cooler than usual, and the engineers, they didn't do their work. They didn't tested the joint at such a low temperature. So I don't know if it was maybe minus 4 degrees Celsius, something like this. Okay, it was not tested. It didn't. It was not tested by the engineers or by the manufacturer of those joints. So because it was so cool, the joint was so much contracted so much that it broke, and that caused the accident. So interestingly, they didn't understand exactly what happened at first, so they launched an investigation. And Richard Feynman, who was a genius, okay, physician, and he was like, it's very sad the way he died. I think he died from a cancer, but very famous physicist, especially in the domain of particle physics. He has those textbooks, very famous textbooks called the Feynman lectures. So anyway, he led the investigation, and he's the one who understood that they have made a mistake, right? And so at the time, I think it was the president at the time. I don't know who was the president or the government of the time in the US, they told him not to say it out loud, so because it will give a bad image of the US, but he did anyway. So he did speak out and he did explain the physics behind it. And the physics behind it is not that hard to understand, right? It's expansion when temperature increases, contraction when the temperature decreases. And I think it was a big blow in the Space Shuttle program, and it retired a few years after that. You have to check this information. I don't remember, but a few years after that, the Space Shuttle program retired. So it was a big disaster, and it was very sad because you imagine all the kids, watching their teacher and boom. So anyway, that's a tangent. So just to tell you that the importance for engineers to understand expansion, contraction of materials. Okay. So of course, the expansion here, so here we are talking about linear expansion, will depend on the increase of temperature. Okay. But it also depends on the original length. Okay. So of course, if you have that, original length, you're going to have this expansion. But if you multiply the original length by 2, the expansion will be also multiplied by 2. So this slide comes from your book, Johnson and Cutnell, and I think it's a great slide. Okay, this picture explains better than words. So you can try to find on your own the relationship between the expansion here and the change of temperature and the original length. It's a very simple equation. Okay. So you have this equation here. And of course, how much expansion you're going to get depends on the material. Okay. So you have a coefficient here, the coefficient of linear expansion. Okay. It's going to give you the expansion per unit length, per unit, the expansion, the unit will be in Celsius, degrees Celsius to the -1, right? So we're going to have that here. So the best way to write this will be the expansion, so the change in length, okay, per original length. Okay, so it will be the change in length over the original length is proportional to the change in temperature. So it means, so that will be in degrees Celsius to the -1. So let me explain what it means. So let's go back to your book here. You see, so first of all, you have linear expansion, but you also have volume expansion. But you see here for liquid, of course, you don't have linear expansion. It has to be in volume. But you see that for liquid, okay, the liquids will expand more than the solid. Okay, you have more expansion for liquid than you have for solid. So for example, water will expand above 4 degrees Celsius more and more and more and more. Okay, so how we can interpret those numbers here? So for example, here it says gold. Say for gold, you have alpha equals 14 times 10 to the negative 6 degree Celsius. So what does it mean? It means that for an increase in 1 degree Celsius, so if the temperature increased by 1 degree Celsius, okay, gold, is it the linear one? Gold, so if you take a ring, for example, so you have a ring here, so ring of gold is just like, you can cut it here and you just have like a strip here. It's like a gold strip, and it's gonna increase if you increase the temperature. I mean, it will expand. So that equation means that it will expand by 14 parts per a million. Okay, so for example, if you have 1 million millimeter long golden strip, it will expand by 14 millimeter. Okay, or if you have 1 million centimeter long golden strip, it will expand by 14 centimeter. Okay, it will expand by this. So if this is 1 million millimeter, I'm just making up. So this will be 40. Okay, so that's a way to interpret the equation. Of course, if the increase is 2 degrees Celsius, then it will be 14 times 2. Okay, so that will be for the linear expansion. Forgot where the slides are. Oh, I have some GIF. You see here, you increase the temperature, and you see how it's gonna be extended. I don't know if I have something else here, but you get the idea. You see the liquid here will expand in volume if you increase the temperature. Okay, so water will expand if the temperature is above 4 degrees Celsius and increasing. Okay, so you can always find GIF and simulation. So anyway, let's go back. Okay, so here is interesting because you have 2 buildings and 2 slabs of concrete. And because it's going to be warmer, it's a warm day. Okay, of course, the material will expand. But in that case, they are not locked with each other, so they will do something like this, right? It's called buckling. They will be able to buckle like this, to bend. And if you live in the US, you see that a lot, right? Because there is, especially in the northeast, you have huge change in temperature between the winter and the summer. So this happens a lot. Okay, so anyway, they want you to find the expansion of linear expansion of the concrete here. And concrete, so you have to go back to the book here, and concrete here is 12 parts per a million per degree Celsius. So 12 times 10 to the negative 6. So you can stop the video. Right, so first is 25 degrees Celsius and everything is good. And now it's gonna rise to 38 degrees Celsius. So it's a huge variation in temperature just in a day. Okay, so it's gonna be 38 minus 25. Okay, so that will be the change in temperature. Okay, so it's gonna be 1, that's 13. So 25 here, 38 here. Okay, then alpha will be 12 parts per a million, or 12 times 10 to the negative 6. Okay, and you see here the initial length, okay, is 3 meters. So you can find delta L equals the initial length times alpha times delta T. Okay, so it's going to be delta L equals 3 times 12 times 10 to the negative 6 times 13. Okay, so you can plug that in and you get 4.68 times 10 to the negative 6 meters. So the final length here will be 3 plus, so it's going to be 0.0000468. So let's see. No, that's a 4 here. Okay, 1, 2, 3, 4. So it's going to be 3.0000468 meters here. So you say, okay, that's nothing, right? Looks very tiny. If you convert that to centimeter, it's going to be 0.0468. It's nothing. However, let's find this. So they don't go into each other. You know, they're going to buckle. Okay, they're going to bend in this direction here. So we can find y. So that's the next question. Can you find y? So you can use Pythagorean theorem in this equation. So here you have the hypotenuse 0.00468. Okay, so you can get your calculator. So it's going to be, you have to take the hypotenuse square. So 3.0000468 square. Okay. And then you subtract 3 square. Okay. And then you take the square root of that. So you use Pythagorean theorem and you get 0.05. Okay, so y equals 0.05 meter. So that will be 5 centimeters, right? So it's like this, right? 5 centimeter is not to be neglected, okay? It's significant, right? So it's about this. So it's a lot, okay? So that's why engineers, or civil engineers, they have to think about it. You cannot neglect that. Okay, so you have the steps here. Let's see. So this example, I'm going to leave it for, I'm going to skip that for now. Okay, so this is also interesting. And that also comes from your book. Okay, so it's built on the previous example. So here, the slabs were allowed to move, okay, in the vertical direction. But what if it cannot move? Just wanted to make clear the strain is delta L over the initial length. So it's the proportional change in length. Okay? And then this is a constant. And that constant for steel is 2 times 10 to the 11 Newton per meter square. So it will be the force that has to be applied per square meter if for a strain of 1. So delta L over L sub 0 equals 1. Okay, so it means this is very much like Hooke's law, except here the spring constant depends on the shape, for example, of a spring, because very stiff spring will have very large K, whereas in that case, the Young's modulus only depends on the material. So it's like the same thing, but written in a different way. So it's mostly used in engineering. So anyway, so that will be the stress, and that's the question why we have. And also we have that the change in length over L. So the proportional change in length. Okay, so how many parts will be stretched will be equals to, so we have the alpha, which is the linear uh, expansion coefficient, times delta t. So you have two equations here, right? So you can see if you can do it, you plug that into there. So you can pause the video to do the numerical solution. So you have the stress, okay, is actually, okay, so how much force has to be applied per unit area? Of course, it's going to depend on the temperature and on the material. Okay, so stress, it's going to be the Young's modulus of steel, so 2 times 11 times alpha for steel. It's going to be, you can look it up here in the slides. Steel 12 times 10 to the negative 12. Is that right? 12 parts per million. So that's going to be 12 times 10 to the negative 6. And then here you have the change in temperature, which is 42 minus 23. Okay, so let's see if I get the right answer. So that's the Young's modulus, 2 times 10 to the 11, times alpha, so 12 parts per million, okay, times the change in temperature, which is 42 minus 23. Okay, so you get 1, 2, 3, 4, 5, 6, 7. So 4.6 times 10 to the 7. And that will be Newton per meter square. So that will be the pressure, right? When you have force per unit area, it means pressure. So it means it will be the pressure applied to balance out the expansion. Okay? Counter interact the expansion. So let's look. So if you take your book, you have the solution step by step. Sometimes they put so much details that it could be more confusing. But you see here, you have the solution there. And if you go back to my slide here, okay, you're gonna have also the solution here. No, you don't have the solution. Yes, you do have the solution. Okay? There is not much explanation, but I think you understand. Okay, so this is one of the application. Different material will not expand by the same amount. So here you have brass and you have steel, but we already discussed that in the previous video, brass and steel. If you look it up here, the coefficient here, you see brass, okay, and steel is over there. So you see there is a difference between them. So this one will expand by 19 parts per million. And this one will expand by 12 parts per million. So this one will expand more when exposed to heat than this one. So let's go back to the slide. So this is the application of bimetallic strip, and we already talked about this. You found them, for example, you find them in thermostat. That will be an application for that. But you see, you have brass steel. When it's heated, the brass, you see, will expand more. So it's going to bend in this direction. You can see that because if you think of a circle, you see that this one will be longer than that one. And then you cool, you see that now the brass will be, the brass is here. The contract more, it will contract more than the steel. Okay. I think there is a short video here. Not this one. This one. I recommend this video too for physics.
This is these kinds of strips are used for switches, thermostats, this sort of thing. When you heat the strip, given the fact that the two metals will have different thermal expansion coefficients, one will expand more than the other, and it will curve, the strip will curve. So I'm heating on both sides to convince you that I'm not cheating by just heating one side and having it expand. So that is a bimetallic strip.
Okay, that was just a demo. And then, okay, we talked about that. So one very famous application will be for switches, right? So you see electricity here is flowing, going through one strip, going through the other strip here. No, it's not a strip here. It's just like conductor. Then this is the strip here. Okay. And when it gets hot, it will bend in this direction. When it reaches the high temperature, it will bend in this direction. So it will open the switch and the machine stop working. So it's a nice application. Now, here, linear expansion, especially in the northeast, when you have extreme change in temperature between summer and winter, you see when it's start to get very, very hot outside, it's sagging like this. Okay. It doesn't look very good. Okay. So the interesting thing also is, the expansion of holes. So this is not that intuitive, but you have this very famous experiment, and I will show it to you, where you have for example, you have a ring. So this is a linear. We're going to talk about linear expansion. Okay, so there is a ring, and you try to have like a sphere going through, and the sphere cannot go through. The question is, when you're going to hit that ring, what's going to happen? Is the hole, so this is a hole here, will get smaller or it will get bigger? So you can think about it. I will show you I'm going to show you the demo.
Had a tile inserted into the hole. Really cool. Another demo. This is a demonstration of thermal expansion. I've got a torch here. I've got a ring and a ball. And the ball does not easily fit inside of the ring. I'm going to heat the ring up and expand it with the torch. And
you see it fits. So it's a very famous classical experiment. By the way, they are also using the same book as us, right? Cutnell and Johnson. So if you want to think about that, because it's not very intuitive, imagine you have a ring here, right? Now that ring this is a linear dimension. So you can cut it here, right? So it will become like a strip like this. So what's going to happen to it if you increase the temperature? So it's going to increase in size, right? So now that ring is going to be larger in diameter. Okay, so when there is expansion, everything will expand. All the dimension will expand. So like, let's say you have a golden ring. Okay, let's say the diameter of the ring is, I don't know, 1.5 centimeter. And now you increase the temperature by, I don't know, you go somewhere very hot, 35 degrees Celsius. That will be the change in temperature. The linear expansion coefficient is 14 times 10 to the negative 6 degree by Celsius, so 14 parts per million. What's going to happen to it? Okay, if you expose the ring to this change in temperature, okay, so you're going to have delta L equals initial length times alpha times delta T. Okay, so you can do the computation. It's quite simple. You don't have to convert because the final unit will be in centimeter. So it's going to be 1.5 times 14 times 10 to the negative 6 times 35. And you get something very small. Nevertheless, finite. Okay? So if you have a conceptual equation, what's going to happen to the hole? Everything expands, including the hole. And it's interesting because something will happen with cavity. So if you have a volume here, and there is a hole inside, right? So there is a cavity here. Like it's like it's solid here, but there is a hole inside. Then it will expand, but the cavity here will expand also. So it works like a photographic plate. So, okay, everything will expand in proportion. So this one, even though now we are talking about a volume, so it will be bigger, it will expand because of the increase of temperature, but the hole inside will also expand. It's not going to shrink. So you have a larger cavity inside. So that was a big deal in the tank for gasoline, for example, right? In the older car, that was an issue, right? Because if you have like inside, so you have, remember the liquid, okay, will expand more than the volume here. So there was an overflow of gas from the tank. Okay, so I think there is an example here. Okay, so let's look at the volume thermal expansions. I don't know why I skipped this slide. So it works exactly the same way. If there is a change in temperature, a volume will expand, right? Not as much as liquid, but it will expand. So if you look at the coefficient here, you see the solid will expand as well. But for gold, okay, you see here it's 14 per million, and here you have 42. So it's at least 3 times more. Same thing here for lead. You see the solid expansion is always more. Aluminium, here you have 70 and here you have 20. Okay, so it's more than 3 times. actually it's about 3 times. Forgot to mention that. But if you try to find the ratio between here and there, it's about multiplied by 3. Between here and there, it's about multiplied by 3. Between here and there, it's multiplied by 3. Okay, so if you look at this equation over there, you see you have I lost my slide here, delta V, so the volume increase over the initial volume, okay, is proportional to the change in temperature, and you have a coefficient of volume expansion, the one that you see here. And you have a ratio about 3. So it means beta is about 3 times alpha. So you can show that mathematically, but you can also show that you can make a drawing here. And you see that if you increase the linear dimension by 1/10, right? So just 1/10, 1/10, 1/10, 1/10. Okay, so because you increase the temperature, so this linear dimension here, which will be the height increased by, that will be 1/10 of this length. So that volume will also be 1/10 than this volume there. And the same thing for this dimension here, right? So because you increase the temperature, this dimension also is going to increase. Okay, so this volume here will be 1/10 of that volume there. And I'm missing one more. So this dimension here, which is the width or the length, whatever, also increase by 1/10. 1 in 10 parts, for example. So you see you have 1, 2, 3. Okay, so if the dimension increased by 1/10, the volume will increase by 3/10. Okay, so that's one way to think about it. Otherwise, you can look it up, and there is some math. You can show it going from 1 dimension to 3 dimension. You can look it online. Okay, so we have this equation there. So for example, here it's a reference to back then. I don't know if you have that picture somewhere here. So here you have gasoline. Gasoline comes from a tank, and the tank is underneath here, inside the ground. So the tank could be at 10 degrees Celsius, okay, because it's cooler inside the ground. And then all of a sudden gasoline comes here inside the tank, and now the temperature becomes 24 degrees Celsius. So the gasoline is going to expand. So now we have ways to deal with it. We have a special container for the overflow, but back then the cars didn't have that, so it was overflowing, and then you have the smell of gasoline, so it was not nice, right? But anyway, it has been solved since then. So you can find how much overflow, okay, how much gas will get lost because the liquid will expand. And for gasoline, you have 95 parts per 10,000 in volume. So you can use the equation. Okay, you can use the equation. Delta V equals initial, and then you have a beta and you have a delta T. Okay, so you plug in. Or what you can do, you can just you can say, so that's one way you plug it in. So that will be 20 gallon, and beta will be 95. So 95 times 10 to the negative 5. The increase in temperature will be 24 minus 10. So delta V will be And you keep gallons. So the answer will be in gallons. So 0.27 gallons. So it means that 0.27 gal. So it's about 1 quart, right? So it was really overflowing. Now, the different way to do it, and you can also say like this. You see, expansion of gasoline is 95 parts per 100,000 for 1 degree Celsius. For 20 gallons, it's going to be 20 times more. And for an increase of 14 degrees Celsius, you multiply by 14. Okay, so you can do the computation quicker. So that comes from your book, and it's a bit challenging, not that challenging, but it takes you to the idea that, so in that case here, with this problem here, we neglected the expansion of steel, because here steel will expand also. Okay, so it means your reservoir, your tank will also expand, and the gasoline will expand. But we neglected the expansion of steel, because there is a ratio here of 10, right? Even more. So that's more than 10. So then we neglected that expansion here. But that problem here does not neglect. So it takes you to the idea, and that also from your book, that this is the tank of your car. Or I think they talk about another tank, but let's say it's your car. You have a cavity inside. So the cavity inside will also expand. So it's good, because then it will limit the overflow. You see, if there is an overflow because of the gas, and this is expanding as well, you are not going to have as much overflow. So this is the idea here. So now we have, it's not a tank, it's a radiator, and you have a coolant, a small plastic container coolant reservoir catches the radiation fluid that overflows. So here, the coolant is inside this radiator, and when it's getting very hot, the coolant will expand. So then you will catch it in that overflow reservoir, but the radiator also will expand, right? So it will balance out, and it's made of copper. So you have copper, and you have the coolant, and the coolant, you know the expansion. So you can stop the video and try to do this one. Okay, so it means not only the gasoline, it's not the gasoline, it's the coolant that will expand, but you also have the reservoir, the radiator that will expand. So then what's going to happen here? It will overflow. You're still going to have some overflow here. So even though this is expanding, you're going to have an overflow here. Of the coolant. So this is the coolant. And coolant, sorry. And you have a reservoir here to catch the coolant. Okay, so you can, so this is the example here. It's from your book again. And now it's a radiator. The radiator is made of copper. So it will expand when it's going to be hot. And inside that radiator, you have a coolant. So it's a liquid. And the liquid is also going to expand, but it will expand more than the solid. But nevertheless, the solid will try to accommodate the liquid a little bit. And what it cannot accommodate, the liquid will overflow in this reservoir. So if you look up here, you see that copper will expand by copper in volume. We are talking about volume, will expand by 51 parts per million, and the coolant will expand more, right? The coolant will expand by 4 times 10 to the negative 4 parts per. So, you can even neglect this expansion, but we won't, because that's the problem. Okay, so this is the expansion for the coolant. Okay, so this is why you have an overflow reservoir. So you can you can stop the video and try to do it. Once you understand what's going on, it's not that hard. So for the coolant, let's do the coolant expansion. So the coolant is here, and then it will overflow because liquid expand by a lot. You see, 10 to the negative 4 is a lot. So you have delta V equals initial volume times beta. So that will be that coefficient here times the change in temperature. So delta V equals the initial volume is 15 quart capacity. So quart is the volume. Beta is 4 times 10. No. 4 times 10 to the negative 4 times the change in temperature. So we go operating temperature 92 minus 6. So I don't know if we do the math. So 15 times 4 times 10 to the negative 4 times the change in temperature. So 92 minus 6. And we get about 0.1, 0.5 quart. So half a quart. So it's not negligible. And now the radiator, which is made of copper, will also expand, but not that much. So that will be the expansion for the coolant. Now let's see for the copper. So copper beta is 51 times 10 to the negative 6. Okay, so it's not that much. So let's see the expansion. So it's expanding, so it's trying to accommodate the liquid, but it will accommodate a little bit, but not that much. So it will still overflow here. So delta V will be initial. So the cavity. So it's the cavity, right? The cavity will expand. That's the idea. The same way the hole expand, a ring expand in 3 dimensions, like this here, the cavity will also expand. So let's see by how much the cavity inside will expand. So it will be initial is 15 quarts. So that's the volume of your cavity, which is the volume of some of the liquid before it's overflowing. So 15 times copper, 51 times 10 to the negative 6 times the change in temperature. And we get, so 51 times 10 to negative 6, this is 86 here. And we get 0.066 quarts, right? So it's about 10 times less than this. But if you want to be accurate, to see what's that volume here, so you have to do this minus that. So you have to do that number here minus 0.066, 0.45 about. Inside. So the whole idea is that cavity expand. Okay, so if you have like a volume like this, and inside there is a cavity, okay, so it can accommodate a liquid. It will also expand, even though not that much, but it will expand nevertheless, right? It will become a bigger cavity. So that's interesting. And so we already discussed this interesting case for water. For any other substance in the liquid state, as you increase the temperature, the liquid is going to expand more and more and more. And liquid expand more than solid, as we have seen previously. But water is special because the solid state is less dense than the liquid state. And in addition to that, when the water is in liquid state, you see that first it will contract when temperature goes from 0 to 4. So the density will increase because it's contracting. And then as you increase the temperature, then it will behave the usual way. It will expand again. So the volume will increase. So the density will go down. And when you go from liquid to solid, again, it will expand instead of contracting. So ice is the solid state of water, and instead of contracting, it will expand. But this is good for life, right? As we have seen at the bottom of the lake, even though it's very cold outside, it's always 4 degrees Celsius because 4 degrees Celsius water between 0 and 4 degrees Celsius has the largest density, so it will sink. This layer will be at the bottom. Okay. In addition to that, here you have 0 degrees Celsius. Maybe it's going to be minus 10 degrees Celsius here. And you have a layer of ice that will float since the solid state has less density, so it will expand more. So it means it's like an insulation layer. Okay, so this is very special because that's how we have life on Earth, right? So during the summer, nothing special here. You have 22 degrees Celsius, layer above the 20 degrees Celsius, above the 18 degrees Celsius, and so forth and so on, because this one will be expanding more than that one. Okay. Then comes fall. So when temperatures are going to fall here at the top, when it's going to reach 4 degrees Celsius, it will sink. Okay. So this is called the overturn. And when this layer will be less than that one, it will also go below. This one will go below, this one will go below, and so forth and so on. Okay, and then we get winter. You really have to get to everything 4 degrees Celsius. Okay, if it's really, really cold, but by then spring comes. And spring, you also have an overturn again, because the top layer will be above 4 degrees Celsius. The top layer will be 4 degrees Celsius, so it will sink. Okay, so you have another turnover. Okay, I think this is the last video of the series, and that's it.